Good morning, everyone. Welcome to this webinar. Welcome to the 40th ETP4HPC webinar. Can you imagine 40 webinars? That's wonderful. So I'm Pascal. I'm ETP4HPC's communication manager, and my colleague Gabriella is also here to help run this webinar. For those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC. We are a private member of the EuroHPC JU, and our mission is to propose research priorities for Europe in the area of HPC. And that's just what we are going to talk about today, because we are going to talk about two topics from our strategic research agenda. So, our recommendations concerning AI and foundational models and hardware components. So before we delve into today's topics, I have a couple of practical information for you. This webinar is recorded and you will receive the link to the recording tomorrow, normally. This webinar is in listen-only mode, but you can use the GoToWebinar control panel that's shown here to ask questions or to download handouts. So you can submit questions at any time during the presentation using this question panel, but we will tackle them at the end. I will share the questions with everyone so you can see what's going on, but we will address them at the end of the session. And so the handouts today, we have put the two white papers that we are addressing today, as well as the slides. So there are 4 handouts today. So our speakers today, we're very happy to welcome 4 speakers. So first of all, Sai Narasim Hamurthy, he's the
Hello.
SRA leader. He will say a word about the SRA and today's topics before we get started. Then we have Marc Duranton from CEA, Craig Prunty from Cyper, and Andy Forrester from HypeAccelerator. So that's very simple agenda. Sai, did you want to say a word of introduction today before we hand over to our speakers?
Yeah, of course, Pascal. Thank you. Yes. So just as a reminder, we released the SRA in January, and post the SRA 6 release, we've been busy releasing a lot of white papers. So we really at the very as soon as we released the SRA, we released the first set of backing white papers corresponding to the SRA, and now we are releasing in the process of releasing so-called agile white papers on different topics. So we have covered we have been introducing these topics to you, the topics that we have covered in the backing white papers, in these webinars. So we have covered a lot of topics like system architecture and system software components and things like that. So today we are going to be covering two really important topics which would be of keen interest for you. The AI and foundational models and the system hardware components. So I'm very pleased that we have Andy and Mark and Craig here. So I'll very much, look forward to the discussion and also any questions you may have. So yeah, please go to our website and download the SRA and the white papers. So I really encourage you to do that. Yeah, back to you. Yeah, Pascal.
Thank you. So in the meantime, Mark has shared his slides. Wait a minute. No, yeah, that's better. We can see your slides, Mark,
Okay,
in
so
slideshow
where do
mode.
we start?
Yes. So hello, everybody.
So
Welcome.
the floor is yours.
Great.
Craig,
So
Mark.
thank you. So in this presentation, we want to cover one of the elements in the SRA6 hardware components. We'll talk a little bit about the organization of the SRA6 in the beginning of this presentation. It's Marc Duranton. Just go back one sec, Marc. Marc Duranton and myself are presenting. We also mention here Denis Dutoit from CEA. Many of these slides and much of the discussion we have is including Denis, so it's important to mention him in this presentation. We don't call out every slide that he at least developed or has the basis for, so we prefer to call him out at the front of this presentation. So thanks for your help, Denis. Next. So here this is the matrix that we look at in terms of the SRA6 itself. So Mark and I were chairing the hardware component, the system hardware components group. So that's one of the research domains, which you see down the right. There are also thematic trends. And so what Andy's going to talk about later is the AI foundational models, which cuts across all of these research domains. Next. So we've seen a sea change in the last 10 years in terms of hardware components. So you're seeing the rise of accelerators, and this has a big impact both in terms of efficiency, but also in terms of software. You see ARM processors coming on the market, so it's not just x86 anymore, which means you have many people building processors, notably the exascalers, AWS, now Microsoft, Google, and the more people who are involved in developing an ISA, the more that ISA has a basis in terms of the software ecosystem, which is fundamental for a server processor perspective. So the interconnect technologies, we need more and more bandwidth, better and better latency. We see AI now in HPC. It's a fundamental part of HPC, but then this drives, where is the precision? Is it 64-bit? Is it 4-bit? Is it somewhere in between? We see the slowing of Moore's law in the sense that you see processing nodes now are more and more expensive, and you get less and less gain for moving to each advanced node. And this then is driving advanced packaging and chiplet solutions. So in addition to the cost of reticules, and we're hitting now the size of reticule limits. And on top of all this, then systems are growing in size, so there are also reliability concerns that we have to address. We'll talk about all of these in this presentation today.
So just to take a little bit back view of the progress of the computing in the last 5 years, the last 20 years. If we compare the performance of a Blue Gene in 25, it was 280 teraflop. So now we have El Capitan, which is still the top of the 500 with 1.7 exaflop. So that means that we have an increase of performance of more than 6,000 times in these 20 years. And in terms of energy, so Blue Gene was 1.4 megawatt, and El Capitan is about 30 megawatt. So that means that it's an increase of energy demand of 21, but globally for energy efficiency, it was a ratio of 300 in 20 years. So just to make comparison on other industry, so for example, for automotive industry, the fastest car in 2005 was the Bugatti Veyron that was able to drive at 400 kilometers per hour. If we get this 222 times acceleration, we should have now the Star Trek Enterprise going at 8.5 times the speed of light. So just to give you an idea of the tremendous performance increase of this technology. And this was done also in other domains, like for artificial intelligence. And this is also very important, the energy efficiency, because what is important is not only the performance, but the total cost of energy, so the of ownership. So the cost it costs to have this system. So if the model were available in 2017, which was not the case, you could see here in the slide that the energy requirement would have not been possible with the accelerator, so the GPU at that time. It was only in 2020 with the progress in energy efficiency of the GPU that GPT-3 was able to be released. And we see a strong correlation between the generation of this large language model with the generation of GPU. So it's very important. And you see, this is only energy efficiency, so that's basically 350 times in 8 years. But in raw performance, this is also nearly 1,000 times in 8 years. And you see here in this slide that it's not only Moore's law. So you see in red that Moore's law has only a small contribution to this. So the main progress is due to the architecture and of course of data coding. So you see that in 2016, LLM was mainly done in floating point 16. So now it's more in floating point 4. That also triggers some kind of problem, because as artificial intelligence accelerator are the mainstream in the market, they will support perhaps less and less floating point 64 that are required for some simulation. That will become a big problem. So you have a solution like emulation, like the Ozaki Scheme 2, that allow to make emulation of floating point multiply with integer. So that's a problem that we start to see in the use of HPC with 64-bit precision. So the challenge we have is how in the next 20 years we being able to pursue these trends.
So beyond that, we see scaling in the processor elements themselves, and you see scaling of compute. And in HPC, this was partly driven by LinPack, because LinPack is quite often the element that's used to judge a system. So, but this is also driven by just the need for compute in general, that it's scaling at a very high level, but the interconnect and memory capacity is not scaling at the same speed. And this is leaving a gap in terms of how you can access the different component elements in compute. If we look at this now from an AI perspective as well, we're seeing a growth in an exponential growth in the actual AI model size itself, and we're trying to scale the compute to address that. But again, interconnect and memory movement, it's a higher and higher cost, and it's falling behind. It's a gap that's growing over time. One element on top of this that we see now with the growth of large systems and large processors is reliability. As we grow the reticle size, we start to go down lower and lower in nodes. And these advanced nodes, even at high altitudes in places like Denver or on mountaintops for observatories, we already see that radiation can have an effect on the processor performance. But the other effect we see is with large systems. Now, statistically, you have many more elements in the system itself. And so statistically, you're going to see more errors across the system as well. So addressing reliability in these larger chips and larger systems becomes very important. Here's a slide that we've shown in the past. We have some updates to it here, but if we look at the evolution of compute elements themselves, again in the 2000s we had single core, single thread. We moved to multi-thread because we ran into a frequency wall. So we couldn't scale the frequency up anymore, or not efficiently, not effectively. So we went to multi-core. Again, there was a big software burden to pay in going to multi-core. The software had to be redeveloped for multi-core, and that took some amount of time. Then we started to run into limitations in terms of power. So we moved to heterogeneous architectures, essentially acceleration. And here again, there's a big software cost to pay. But now we're moving into, let's say, it's a cost wall, it's a reticule size wall. And we see people talking about this idea of a chiplet marketplace, where you can put chips together based on, in today's, most people assume it's UCIe interfaces. We assume that's going to be the future. The challenge here is that there's a lot of standards that don't exist today. So we see this chiplet architecture idea. Today it's between a single company or one company developing chiplets, or maybe one company working with another in close proximity and sharing all the requirements for elements to work together. The other big element here is software. But what it gives you in return, if you have scale, you can share the cost of a solution. You're seeing chiplets become the new IP, especially for elements that are vanilla but hard to do. Let's talk about PCI Express, for instance. PCIe I/O chiplets is a great idea because they're hard to make. PCIe is hard to make. It's hard to get it right. At the same time, it's not a differentiated solution. Your PCIe Gen 5, your PCIe Gen 6. So we're seeing that chiplets are becoming the new IP. And over time, we'll have a chiplet ecosystem or a chiplet marketplace where you can just blindly put two chips together. But right now, you have to work in close proximity with other companies. That's where we see the future going.
So
Next.
let's dig a little bit into more into this chiplet. So we see the evolution from classical Moore, so where we put more transistor and increasing the frequency, to SysMoore, where we have more, as Craig said, system on a chip. So the computing cores, the accelerator are becoming function in a global system, and also increasing in terms of dimensionality. So the classical monolithic SoC were in 2D. So now we are starting to stack various architectures, so processor, memory, and things like that. And this approach of a chiplet on interposer has several advantages. The first one is, well, when you make a monolithic, a big die, composed of processing, memory, IOs, the technology is not optimized for its functionality. The technology for processing is not exactly the same than for memory or for IOs. So that means that you have an overall average performance on your monolithic die. If you are using chiplet, each one using the best architecture for the functionality, then you could get the gain here. You also get a cost reduction because you have the right silicon node per function. And also, instead of very big silicon, which when you have one fault, the complete silicon is dead and you have to go to the trash. When you have smaller part, so the yield is higher. So the probability of error is lower. So that means that the functionality could be at lower cost because globally you have a higher yield in your system. And also, as Craig said, with this approach, you have some kind of modularity. We could see that the interposer, which support all the chiplet, are the new PCB in the SysMoore area. So that means that if you have an ecosystem of various IP provider, of various chiplet provider, you could make a new architecture more tuned to your application, which are, by the way, more efficient in terms of performance, in energy, and in things like that. And also in terms of cost, because each time you don't have to make a new tape out of very large or very complex system. And also, thanks to the reuse, it should be a faster time to market and possibly a reduced sourcing dependencies, because for the same functionality, you could change for various provider. But as Craig just said before, this is just emerging, and we need to have this initiative to create open platform, and that's created this new market of a chiplet and interposer. And also, this is ready for the future. So, Craig, you have something you want to add?
One of the things, yeah, just on the chiplet on the slide before the paradigm. One of the things that is fundamental here is if you're looking at different kinds of accelerators you can put in a package, the CPU becomes the orchestrator, and it should hide the software complexity of the accelerator. That's going to be fundamental. So working as much as possible on open software and making sure that the CPU is what the user sees will give the best out-of-box experience. And that gives opportunity for different kinds of accelerator in package as well.
Yes, indeed. It's also a change in the programming paradigm, where before the CPU was doing most of the functionality. So now it's only an orchestrator to call the dedicated architecture for each functionality, for floating point, for EI acceleration, for I/O. So it's why you see an emergence of a lot of new names like GPU, like NPU for neural network, like a DPU for data processing unit, or IPU for infrastructure processing unit. So all this chiplet or functionality will be called by the CPU that orchestrate all them together to have globally a better efficiency of your complete system. But of course, one of the key system, a point for the system is to have a tight integration. So that's try also in the software to have some new model of shared memory and things like that. So that means that you need to have virtualization of several chiplets into one global system. That means on the hardware to have more NIC, network interfaces, and also to have better bandwidth for the communication. And this is also possible because the chiplet could be also in silicon, but it could use photonics to be more efficient in terms of latency and bandwidth of communication between these chiplets. And here we see the beginning of real co-design between technologies, between, of course, photonics need special requirements. So, for example, if we want to make multiplexing of various light frequencies, so of various color, if you want, to superpose on the same hardware some kind of parallelism with the frequency, you need to have a thermally tuned system. So that is really technology. You need to make a special design that accommodates how to link your chiplet with this interposer. And of course, you need to have a system point of view. So that's really drive more and more in this co-design approach.
So as Mark said, now we're looking at more and more kinds of accelerators enabled. Ideally, the software is hidden behind a CPU, but as you have systems built up of acceleration, then you need a co-design approach. So you start at the application level and you say, what does my system need to do? What acceleration do I need in my system? Then below that, you look at the algorithms that are supported on this. They will be dependent on what kind of accelerators you have. Ideally, you're hiding the software, but again, it's complex. The programming languages below that, and as we go down the value chain, as we continue down, of course, the software stack, coding, how you code the data, then it gets down to the baseline architecture of both the chiplets themselves and the system, the chiplets, how they fit together. This is a difference now because you're starting to look at where do I segment the chip based on chiplets, as opposed to necessarily just the functions I have in the chip, and then they may be different. And below that, then what kind of technologies, what kind of base technologies, whether it's manufacturing, whether it's raising the TRL level on photonics, things like this, all these base research technologies will be then driven by where can we go in the market, where are the needs of the customer at the application level driving all of this. So again, from a co-design perspective, as you have more and more acceleration enabled, we'll see that we're going from application to software to data coding, and this will then drive where we actually put the R&D on technology. It's a large spiral that we see, and people talk a lot about co-design, but it's going to get more and more important as we have more and more acceleration in the system.
Yeah, so in view of time, we have to limit to some highlight of what we work on in the SRA 6. So you could refer to the SRA 6 document and also in the white paper. But for example, all the topics that enter now into the HPC domain, that more from the, let's say, if we have a trend as HPC as a service, so that means that more security should be embedded into the system. Supply chain is also a very important thing. If we have this market of a chiplet and interposer, you need to be sure that you have the genuine a chiplet, so to have at the low level some identification of the system is very important. And also reliability, so we touched it at the beginning, but imagine that if we have system composed of millions of accelerators, the mean time between failure could reduce to few minutes or even lower. So this is a big challenge for the very big system of the future. So please have a look to the SRA, to the white paper, and on the white paper you could download it from this web interface today. So I think it's all for us. So let's go to the next talk.
Thank you, Mark. So I will ask Andy to share. So while Andy is sharing, I just wanted to remind everyone that you can download the presentations from the, I think it's called materials section. Yes, we can see something, Andy, and you can ask questions in the question menu. So.
Thanks very much, Pascal.
Okay, can you go maybe to, you're not in slideshow mode. We can see just the regular pop. Okay, that's better.
But now I can't see
Perfect.
my notes.
Ah,
So
uh,
I will have to go back.
okay, but we can't see the full slide, Andy.
Yeah, that's okay. I'll just bear with me a second. Sorry about this, everybody. Can you see the full slide now?
More or less, yes.
Is everybody okay?
Yeah.
Right. So, good morning, everyone, and thank you for joining my portion of today's webinar. My name is Andy Forrester, and I'm the co-lead of the AI and Foundational Models Working Group at ETP4HPC, in conjunction with my esteemed colleague Maria Perez. In this session, we'll walk you through the key findings and recommendations from a recent white paper, which Pascal and Craig and Mark introduced as part of the SRA 6. In our presentation, we'll examine how the rapid evolution of foundation and frontier AI models.
Sorry, Andy, you're showing
Yeah.
slide 4. Is that correct?
No, that's not correct.
I thought it might not be.
There we go. Excuse me, everybody. This is the first webinar I've ever done, so I'm a bit
So
of a
now you're
novice.
showing slide 2, okay?
Slide 2, yes. So this is just my
Okay,
introduction. Yeah.
right.
So just to recap, we'll examine how the rapid evolution of foundation and frontier AI models intersect with global HPC infrastructure, and we'll discuss why Europe must take a lead in shaping this new computational paradigm. So, can we start with a quick definition? Foundational models are in effect large-scale, pre-trained neural networks that serve as a base at scale for a wide range of downstream tasks. These models, such as ChatGPT, Llama, Gemini, and Claude, are continuously fine-tuned for a very, very broad range of use cases.
Andy,
That
sorry to
said,
interrupt. So,
yeah,
I think you're looking at slide 4, right? We see slide
no, this
2.
is just my introduction.
Okay, great. Thank you.
Sorry,
Sorry to interrupt. Yeah,
that's all right.
sorry to
That's
interrupt,
all right.
please.
We in Europe, we're standing at a crossroads. We have the talent, the infrastructure, political and policy foresight to lead the global effort, but it needs coordinated investments in research, ethical AI, compute resources, and data strategies. So what our white paper has set out to debate is what is the technological and strategic roadmap to achieve these key objectives. So let's look at AI at scale. So AI at scale refers to more than just training large models. It's about their resilient deployment and integrating them into production grade workflows that are accessible to all. We're seeing an increasing demand in real-time inference, embedding models into simulation workflows, autonomous experimentation, and dynamic decision making, from the very simple to the highly complex. This is continuously putting stress on our compute resources, the compute architectures, memory, and data storage globally. This is especially the case for sustained inference, not just one-time training, and those HPC systems and GPU accelerated clusters must evolve to be able to handle our constantly changing nature of our AI workloads, and producing first-class, ethical, accurate results. So let's move on to foundational models. So these models are continuously transforming the software stack. They support a hugely diverse range of data types, including text, vision, in genomics, protein sequences, for example, speech, and time series. And those and their complex attention mechanisms allow for long-term dependencies and context. And that's one of the key reasons why they are becoming so successful. We then look into parameter efficient fine-tuning like LoRa or RAG that in itself produces lower costs of that training, and that reflects back to Mark and Craig's portion of the webinar where they looked at that in highly technical detail, and accelerates customization as well. So let's move on now to architectural innovations. So as we scale up our foundational models, this is continuously exposing our system and infrastructure architectural bottlenecks. We're deploying alternatives like XLSTM and CANs, which are emerging to address long context windows and parallelization. I'm going to refer to co-design. In previous SRAs, we focused on that in a significant way, and that is hardware and software tailored in conjunction with each other for AI. And let's highlight the successes of GraphCore and Cerebrus, and software that leverages tuning, quantization, and low bit numerics. We then introducing partition memory and model parallelism, which I think we will understand are essential at a hyperscale level. So these innovations must be integrated into our post-exascale roadmaps. One thing that is very high on the political and public agenda is ethics and safety in artificial intelligence. And to a substantial degree, the implementation of the EU AI Act addresses the compound risks that ethics and mitigating and introducing ethics and safety produce. So the EU AI Act introduces thresholds at 10 to the power 25 flops, impacting foundation model governance. That represents some common risks. Data hallucination, biased outputs, and reward hacking. So our white paper supports adoption of the area framework. So anticipate, reflect, engage, and then act. But that's just not our responsibility as HPC experts. That's the responsibility of our politicians as well. So, but as technicians, you know, we must at all times promote safety and trust for integration into the HPC design pipeline, not retrofitted after deployment of those models. So let's move on to some applications and use cases. I think we all agree that foundational models are significantly revolutionizing how we work. In healthcare, with diagnostics, drug and pharmaceutical discovery, and clinical text mining. In education, real-time tutoring and automated grading. In smart cities, traffic prediction, waste reduction, urban planning, and in regulation, compliance automation and contract analysis. In fact, the legal provision has been one of the early and major adopters of AI and foundation models. These applications really demand federated, explainable, and highly secure AI deployments. Now let's look at the relationship between quantum and AI briefly. So I think we've assessed that AI and quantum computing are converging. AI is being used to innovate and design quantum circuitry and interpret quantum output. Our quantum methods are certainly going to enhance our classical artificial intelligence in the future with improved optimization and generative capabilities. So off the back of that, we recommend that Euro HPC and Euro QCS align their strategic efforts in co-design, which we reflected on a few minutes ago, shared tooling, and hybrid infrastructure development to avoid silo research and development. Now, if we move into trends and future outlook. So our key trends that are shaping the future can be summarized as follows. So we have AI workloads shifting from centralized training to decentralized inference. Multimodal AI is going to be the norm, combining all those data types, text, vision, time series, geospatial data, etc. Sustainability and energy efficiency is certainly going to be to quote a Star Wars, a Jedi analogy, a first order constraint. And then we are always going to be having emerging societal requirements, and reflecting back on the ethics and safety in AI around interpretability, fairness, and the risk and eradicating the risk of bias. So these trends are really going to redefine what our HPC requirements are going to look like in the future across the HPC technology stack, and policy driven driven from Brussels. So let's summarize our key thematic areas. Our white paper defines priority themes: specialization techniques, RAG, LoRa, and chain of thought prompting, energy efficient and sustainable architecture designs for trillion parameter scale, multilingual AI that reflects our European diversity, IP control, privacy preserving AI, and adversarial robustness. We've all got a responsibility to ensure that AI is reliable, resilient, and compliant. Strategic recommendations. Let's reflect on the core points that we've covered. In the white paper, we offer six strategic directions. Invest in domain-specific foundational models, science GPTs, for example. Integrate and implement federated AI platforms sponsored by EuroHPC. Advance alternative architectures beyond transformers. Establish ethical oversight using compliance and standards such as ISO 42001. Support our tool chains and data sets for SMEs. And finally, bridge the quantum AI gaps through joint development programs. We're coming close to the end of the presentation, so let's look at future trends and vision. Our high impact domains include sciences, aerospace, healthcare, smart manufacturing, and these domains are ripe for foundational model integration enabled by sovereign EU HPC capabilities. And the next step, beyond exascale. Our post-exascale systems are undoubtedly going to need inference first workload optimization, memory efficient training with mixed precision and sparse operations, very high bandwidth interconnects for highly efficient model parallelism, and scalable synthetic data that supports our complex benchmarking frameworks to maximize computational performance. So the aim is to make our AI training and deployment sustainable, sovereign, efficient, and secure. In terms of post-exascale recommendations, let's look beyond 2030. And our technology roadmap calls for renewable power data centers, collaboration at the convergence of AI, HPC, and quantum, transparency by design in AI, and democratized access to foundational models for researchers, industry, and the public sector. Now, in terms of finally, our overall conclusions, I think we all recognize that HPC is critical to Europe's AI strategy. Ethical, secure, and sustainable AI and foundational models require deep collaboration across the board. And Europe has the opportunity to lead globally by aligning compute, policy, and data within its strategic goals. So as a working group, we concluded that the work ahead is going to be challenging. But if we have clarity of purpose and investment through Euro HPC and the Horizon Europe program, we can develop, shape a trustworthy, capable, efficient, sustainable, sovereign AI ecosystem. So thank you very much for your time and attention. The full white paper.
Thank you, Andy.
Okay.
Thank you very much. Yeah, do download the white papers. I mean, they are in the materials section of this webinar, and I also put in the chat the URL of the SRA page where you can find the SRA and all the other white papers. There are 11 of them. Is it 11 or 12? I had a doubt. Do you
Yeah, I think
remember?
it's I think it's 11. I
11,
may be
yeah,
wrong as
yeah.
well. Yes.
So don't hesitate to go there and look at the topics we have already covered and download them. So sorry, I'm sharing the agenda. So now we're down to Q&A, question time. So I see we already have at least one question. So question to Craig and Mark, okay? Considering the gap between memory, interconnect, and compute, which is increasing, will it be good to know what are the ongoing it will be good to know what are the ongoing efforts to address this.
Should I start, Mark? I think we both have things to
Yeah,
say
yeah,
on
please
this.
start, yes.
Okay, so if we talk about acceleration, memory is a kind of acceleration. So looking, there's a bit of an explosion in terms of memory as well. So HBM is certainly one kind that's very efficient for acceleration. I would say that it's less efficient for on the compute side, but again, as we bring compute and acceleration into package, sharing high bandwidth memory and or DDR memory and or LPDDR memory, MRDIMMs, there's a lot of different kind of memory coming. And this will also play a lot into how we segment, how we partition chiplet solutions. What's the architecture that we select? It depends on workloads you're focusing on. So some workloads are more compute intensive. Many today are blocked by memory bandwidth. So there's advances in memory. You even see advances in things like CXL, which is really shared memory across nodes. That's the value you see there. But although the latency is high for CXL memory, the capacity that you can get and share is quite interesting. So this plays a part in terms of interconnect and sharing memory across nodes. So I would say we're seeing a lot of change in the different types of memory available. LPDDR now, you're seeing CAMs come on the market. Those are principally for PCs, but people are looking at those now for even server compute. So I would say that you're going to see an explosion in many ways, and it's going to change somewhat the architecture. The cost of memory movement is high. Do we then look at coherency, in-memory coherency? That's also expensive to do. So these are trade-offs we'll make over time. Mark, probably you have some thoughts on this as well, I guess.
I think also in terms of technology, you will see more and more hybridation of various technology. So we already have system which has HBM on DDR, but you see the memory is a full hierarchy from the non-volatile memory to the very fast SRAM. So here, the boundary between where SRAM is better, where dynamic memory is better, is evolving with the new technology. So there will be possibly in the future a new technology like FIFET, so using magnetic ferroelectric memory that could be very fast and very efficient. Also, you see now that you have vertical DDR, so trench memory. So we have a lot of new memory. And of course, the 3D stacking, when you see on architecture of 3D stacking, then generally you have one layer of compute on 2, 3, 4, 5 layers of memory on top of it. So it's both to increase the capacity of the memory, but also to decrease the distance between the processing and the memory, and to increase the density with this 3D stacking. That's also drive new problem of thermal dissipation and things like that. But there are a lot of work. So you see some forecast for the next architecture that will be really a sandwich where you will have the PCB, then the interposer, then the processor, then 2 or 3 level of fast memory, then a non-volatile memory. So you could have a sandwich up to 10 layer of various layer. And for the ultra dense memory, so the cube that are done, for example, by Micron, I think it's more than 200 die that are stacked together. So you see, we are more and more going also in the verticality to increase this ratio of memory versus compute.
I think that the other thing that, yeah, so processing in memory is interesting as well. That's fairly limited today in terms of the processing, but that's something that's going to evolve over time as well. And what can you offload in the memory itself in terms of compute? Where do you get efficiency there? So, yeah, and the advanced packaging that Mark talked about is going to be very important in stacking. Yeah, yeah.
Thank you, Craig and Mark. So we have several more questions coming in. So first, a question from Gulcin Gedik. Gulcin, I think we met at ISC. So hello, nice to see you at a webinar. So the question is, how do you think the future AI factories look like? It gives the impression that we begin to see AI as a system design rather than AI as a workload that runs on HPC centers. So Andy, do you take that one or?
Yeah, I can take that one. So yes, I mean we treat AI as a transient workload, often, which is often sort of batch process alongside other workloads. But AI factories, I think, in contrast, are designed around continuous real-time learning loops. So data flows in, models are trained and refined, and inference is deployed at scale. And I think we think about these factories having a pipeline as almost like a supply chain with your raw materials, data processing, training, fine tuning, QA, validation, and product delivery, which the AI factories are going to be very good at. I think in terms of core characteristics, we need to reflect back onto the co-design strategy. So AI factories to integrate clusters with ultra-fast interconnect, NVLink switch for HBM memory, and local NVMe for minimizing latency, and composable architectures. Then a multi-tiering of AI lifecycle support, so training, fine-tuning, inference, and evaluation. And then finally, implementing, exploiting sort of federated and decentralized infrastructure where you've got integrated AI factories across countries, each supporting each other with sort of things like sovereign data security, federated learning, privacy preserving computation, and providing future integration points. So I think we're witnessing a rethink of AI infrastructure as a production system, rather than a subset of HPC. So yeah, I think that can. I think that's. I hope that answers the question, Gabriela's question.
Yeah. Okay, thank you. So now we have a question from Thierry Colette. Hello, Thierry. So a question concerning the chiplet. So I think that's going to be for Craig and Mark. Do you plan to push in order to have a marketplace in Europe for chiplet for the edge implementation?
Okay, I
Who
was looking at
takes
the
this
one
one?
on neuromorphic, but yeah, I can
Okay.
maybe. Well, actually, Mark, do you want to start? I started last time.
Yeah, I could start. Yeah, there are several initiatives. So in the chip GU, there is a push to have a platform that help people to use a chiplet and to promote chiplet on interposer. So there is an action here, but of course we need to have a support from industrial and then people. And here I could say that some companies are working on this. And perhaps, Craig, you could go more into this detail because I think you are directly involved in this.
Yeah, yeah. So if we look at this, so people talk about this chiplet marketplace, and they talk about sort of putting Lego blocks together, and this is multiple levels. So the first would be, what are the interconnects? Is it standardized? How do they connect together? And today, if you build two chips blind on UCI interconnects, and let's say you agree on UCI standard as opposed to advanced, so you already know that, they won't work together. There's just too much gray in the spec. So you already have to be working cooperatively today to make sure your chiplets will interconnect. Then on top of that, you have everything from the manufacturing ecosystem has to be in place. What's a known good die? Who's responsible for what? Who's doing the integration? In package, how do you do BIST? Who tests the interconnects? Where's this? What's core zero? I mean, there's a number of things that have to be standardized across this SoC before you can do blind builds and have things work together. And a lot of them aren't complicated, but they have to be agreed. And so there's going to be a period of time during which we create this ecosystem for chiplets, and it's going to be based on people doing it. So today you have single companies like AMD, like Intel, doing chiplet solutions. They're starting to work with other companies in close proximity. But again, they're working together. Everything's defined together. And slowly over time, you're going to see more companies becoming involved. We're going to figure out problems we didn't expect. My guess, this is a personal guess, but I would say that this idea of having a marketplace that works standalone is probably not before 2035, but it won't be a step function. It'll be a continuous continuous movement back and forth. There are things we do well and things we have problems with that we'll discover over time. In terms of edge, I think when we talk about edge, for me, edge is really server edge, but you can talk about device edge as well. All of this will go hand in hand. This is an ecosystem, a chiplet ecosystem that will affect all markets. Automotive could be considered an edge market, to server edge, to device edge. But in every case, and this gets to Fabrizio's question below, there has to be a value. Integrating costs money. Chiplets are more tape outs. So there has to be a value in doing this. You have to have the scale. We're already seeing from the cadences, from the synopses, the IP providers, they're looking at chiplets for vanilla functions. So this is starting to happen, and that's scale because they're scaling across markets, across different elements. Anything that's vanilla will start to become an IP, a standard IP, and then more and more we'll be focusing on the differences, the elements that give us the TCO in the solution, as the chip and chiplet providers. Anything on that, Mark? Anything to add?
No, I think you are correct, but indeed this need to be amortized for several markets. So you could see that if you make a computer and accelerator market, of course it could be used in HPC with very large configuration and things like that. It could be used in different configuration for server, where the ratio memory accelerator could be different from HPC. And it could be also used in the automotive. As you say, it's a new emerging market. So there are several alliances in Asia, in Europe, that work on using chiplet on interposer for the automotive market. So of course it could be the same chiplet than in HPC, but instead of having a 10 chiplet on the interposer, you will have 2 or 4, and also depending on the range of the car that you will have. So this is really this fine tuning that is emerging, that, as we said before, still need a standardization and things like that, because now companies are making chiplet and interposer, but on their own product. So having an interoperability between companies is still the challenges.
Okay, thank you. So I think Mark and Craig, you addressed 2 questions in one go, because this also answered the question from Hans Christian Hopper, right?
I think, well, I'm not sure we had completely answered it, but I think we addressed some of it for sure.
Okay. By the way, hello, Hans Christian. Okay, so then we'll go on to the I'm sorry, we're running a bit late, but I would really like to address the last question. Question on hardware. What are prospects of disruptive technologies such as neuromorphic computing in the realm of hardware?
So you have in the SRA 6, you have a complicated action on a non-conventional architecture that will give you more hints into this direction. But okay, we could try to answer. For dedicated accelerator, this could be the solutions, and that also depends what you call the neuromorphic. So is it using physics to make computation? So here we start having several architecture using optics also to make computation and things like that. So you have more NPU, so more really neural, which are more neuromorphic, and basically using physical phenomena like a non-volatile memory to make computation. But here it works on a small dimension, but still the problem of scalability is here for 2 reasons. The first one is that if you use physics to make computation, you cannot fold in time. So the nice added value of digital technology is that you could make computation, store into memory, reconfigure the hardware, and make the computation again. If it's the physics that is making the computation, it's far more difficult to do that. So basically, you need how many devices as the size of your problem. That also brings the problem of variability. So if you are running more into more analog domain, the variability becomes important. So you see, we have in digital the problem of reliability, but when you are using analog and physics, then variability is also adding to that. So yes, there will be a great hope on this, but we still need some more scaling to these solutions.
Just to add to that on the market side, you're seeing today that large language models and GPUs are pretty much stealing all the oxygen on AI. There's a land race for GPUs today. We expect 2 things to slow that down, or analysts expect 2 things to slow that down, and there are interesting debates about this. One is energy. I mean, you're seeing hyperscalers now buying nuclear power plants, right, to have that enough energy to power their data centers. And the second is data for training. And there are new ways maybe to take data. There's multimedia. There are so that's a debate about whether data will become. It's becoming an asymptotic limitation today, but are there ways around that perhaps? But we expect at the point that we start running into these asymptotic limitations that people will come back to, how am I making money on AI? And this sort of land race for GPUs will slow, and people will be looking at what are the efficient ways that I can do AI. And that's where I think things like neuromorphic will sort of rise back up again. Robotics will have more of a, let's say they'll be more funded. But right now all the funding seems to be going to GPUs.
Thank you very much. Well, we are over time, so I think we will stop for now. I would like to thank our speakers. Thank you very much for your presentations and for tackling the questions from our audience. This was very interesting, as usual. Actually, I thought we'd have questions about AI and none about hardware. And this proved me completely wrong, but well,
Very.
okay.
Yeah.
So thank you anyway. Thank you to our audience also. We'll talk to you again in September. Yeah, the webinars are having a summer break. So have a lovely summer and see you in September. We'll keep in touch and send you an invitation for our next webinar. Thank you
Thank you
and
very
bye-bye.
much.
Bye
Bye
bye.
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 Bye. See you everyone.
Thanks everybody. Bye bye.
I think so.